Well, friends, from today onwards, we enter into a new phase of our discussion. I like to say the basic concepts about the hardware, about the performance a control system is required to achieve, about how to design a compensator to achieve that performance. I like to say that the basic concept involved in the complete process of design have already been taken. The only thing is that one of the routes has been taken, the pole zero route or the root locus method for design has been discussed. Today onwards, in the remaining 6 hours, about 6 hours I think we are left with, in this period we are going to take up the new formalism of analysis and design called the frequency domain formalism. So you will find that the basic concepts remain the same. The only thing is that the interpretation and hence the analysis and design techniques will change. Though the sequence is not this way, maybe the frequency domain was developed earlier than the root locus, but nevertheless the presentation of the subject has been done in a particular way so that the idea of the transient performance becomes clear. You will realize that it is very easy to appreciate the transient performance in terms of poles and zeros, in terms of the root locus plot, because you are able to visualize the transient performance directly in terms of closed loop poles. You will find that in the frequency domain formalism, though the analysis and design techniques are really very good, but the interpretation of the results is indirect. It's not direct as was there in the case of the root locus method. I will say that as far as present stage of analysis and design of control systems is concerned, you consider root locus method, you consider frequency domain, or you consider other advanced methods which you have not studied, like the state feedback pole placement, like the optimal control. Probably the most often used is the frequency domain formalism. The reason is this, that this gives, as it is said, the robust control. The dependence of the frequency domain methods on the model of the system is not that stringent as that of any other method, including root locus. And we know that the model of a system is hard to obtain, so naturally you will like to rely on the methods which do not crucially depend on the model of the system. I like to say that this is the main important reason. Of course, the other reasons will follow, that you will find that the analysis and design in frequency domain is easier comparatively. So these are some of the other advantages, but as I view, the most important advantage of this formalism is the dependence on the model. The model may not be very accurate, still you can get suitably good results, implementable result, while all other methods heavily depend upon the accuracy of the model. Okay? So I will like to introduce, you already know what is frequency response or what is frequency domain. I will like to introduce, just make you recall what is frequency response through this particular simple block diagram. Let us say this is the process, a system you already know, and this system is subjected to an input which is sinusoidal in nature. Let us say RT is equal to R naught sine omega t. This is the input. Now the output, as is known, will have the transient as well as the steady state component. If I consider this system to be a stable system, in that particular case the transient components will definitely die out with time. So it means we will be left with only the steady state component. So if I concentrate only on the steady state component of the response, I say that yt will look like y naught sine omega t plus phi. This will be the nature of yt. So it means steady state response of a linear system described by the transfer function gs is also sinusoidal for a sinusoidal input. The only change is in the amplitude and the phase angle. So if I give you the amplitude y naught, or if I give you the amplitude ratio y naught over r naught and the phase angle phi, for different values of omega, the sinusoidal frequency, you have got the complete input output picture of the system as far as steady state sinusoidal response is concerned. So you see that in that particular case, I will say that the frequency response of this system is given by the variation of y naught over I naught, r naught versus frequency, and the variation of phi versus frequency. Because if this information is given to you, you give me any sinusoidal input, you will be able to get the sinusoidal response of the system at steady state. So I have defined in the process what do I mean by frequency response. So the frequency response for me for a given function Gs is the amplitude ratio y naught over r naught versus omega. It is, you can say, is the magnitude plot or magnitude response, and the other is phi versus omega. With this information, you give me any input, I will give any sinusoidal input, I will give you the sinusoidal output of the system. Okay? And that, let me not go to the details, you know that this y naught over r naught is nothing but the magnitude of G calculated at S is equal to j omega. So I have not to excite the system, but what I want to say is that the frequency response of the system is completely contained in the mathematical model of the system, in the transfer function model of the system. The amplitude ratio is nothing but the transfer function G evaluated at S is equal to j omega. Similarly, phi is nothing but the angle of Gj omega. So now let me put it the other way, that the magnitude Gj omega and angle Gj omega versus omega constitutes the frequency response of the system for me. Okay? However, this point may be clear at this juncture. I know that you already know it, but I like to repeat this. I said Gj omega versus omega, angle Gj omega versus omega. You may plot them and you can get frequency response plots, the graphical picture of the frequency response. Let us say frequency response plots are available. I made a mention that this information gives you the output of the system for any sinusoidal input at steady state. So on the face of it, it appears as if this particular mathematical model, which is the frequency response of the system, is only a steady state mathematical model of the system, is only a model which describes the performance of the system at steady state. Fortunately, the situation is not that. Actually, it is a complete characterization of the system, including the transient response, because you know, given the frequency response through Fourier transforms, you can correlate this to time response, and hence from the frequency response you can get the response of the system to any time function. The only thing is that the time function will have to be broken up into superposition of frequency signals, either through Fourier series if it is a periodic signal, or through Fourier transforms for a non-periodic signal. So at this point, it should be very clearly understood that though all through our discussion now onwards, our concentration is going to be on frequency response plots. But it should be clear that the frequency response plots, though they have been experimentally or otherwise obtained from the sinusoidal response of the system at steady state, it actually constitutes the complete mathematical behavior of the system, complete transient as well as steady state behavior of the system, because Fourier transform is a correlation, is a link between the transient response of the system and the steady state frequency response of the system. I will be coming to this point at a later stage when I want to get the transient behavior of the system, when I want to interpret the frequency response into time domain. At this juncture, I will like to proceed further with this comment that the frequency response plot of a given system is a complete characterization of the system, both the transient and steady state. Okay? This should be clear. And one more thing, as far as the frequency response plot is concerned, experimentally it is so easy to obtain experimental data that suppose you are working, suppose the mathematical model is not available to you. You see, the mathematical model is not available, G is not available to you. What you finally want in terms of control system analysis and design, the magnitude of the amplitude ratio versus omega and the angle of the amplitude ratio versus omega. This is what you need. So, this you can easily obtain experimentally on a given system. If the hardware is given to you, but the mathematical model is not known to you, you cannot proceed with the root locus method. Please see, you will have to first identify the mathematical model of the system, and the mathematical model is nothing but the pole 0 model, is nothing but the transfer function model of the system. But if you go for the frequency domain formalism, if you are given the model obtained by physical laws or obtained by any other method, you can obtain the frequency response this way, or equivalently you subject your system to sinusoidal testing, and sinusoidal testing is easy hardware wise also. Subject your system to sinusoidal testing, obtain the magnitude and the phase angle, use this frequency response data to get the frequency response plots, and these plots which have been obtained directly from the system hardware is a complete characterization of the system. You really do not require the transfer function model or any other model for analysis and design. This is a very important attribute of the system, because the modeling of a system is a very difficult exercise. Even through frequency response, for example, suppose you have got this experimental data which is the frequency response data, and you want to use the root locus method. What will you do? This frequency response data will have to be suitably fitted into a pole 0 model, and that pole 0 model will be used for root locus design. But it should be very clear that this fit cannot be one-to-one fit. You are definitely bound to make errors. So, the frequency response data which you have got, you are getting a pole 0 model because you want to use the root locus method. However, in the process you have definitely made errors, because a complete mathematical model is not possible, a complete fitting will not be possible. So, you are working on an approximate model when you are going for a root locus formalism. But in the frequency domain formalism, since this step in between is not needed, you are directly using the raw data for your analysis and design. Okay. So, I hope this point is clear, that as to what is the, why is this particular approach, the frequency domain approach, is so important for the control engineer. It is really very important, it is extremely important for the control engineer. Not only this, you see, some of the concepts of the performance of the system are well understood from the communication theory. Communication engineers, you see, are happy with these sinusoidal transfer functions, because for them the input is also sinusoidal in nature, or superposition of sinusoidal signals. A control engineer naturally is not necessarily working with sinusoidal input. When we are taking frequency domain formalism, it is absolutely not in our mind that our control system will be subjected to sinusoidal input. It may never be subjected to sinusoidal input. Still we are going for frequency domain formalism because of its advantages. The noise characteristics of a system can best be understood in frequency domain. So, naturally, if I have frequency domain formalism, I can see the noise filtering characteristics more appropriately than its equivalent effect in time domain. So, the bandwidth will be defined. The bandwidth equivalent is rise time, but the rise time of a system really is not a true representative of noise characteristics of the system as far as our understanding is concerned, while bandwidth we immediately appreciate as to what type of noise characteristics or noise filtering behavior the system is going to have. So, it means there are some characteristics of control system behavior which are better understood in frequency domain. So, I like to conclude my statement, introductory statement, with this particular viewpoint, that the root locus formalism is better because the transient response is well appreciated directly in terms of closed loop poles, though the root locus method relies on the accurate mathematical model. The frequency domain method is better because it gives us the noise filtering characteristics, it can work on less accurate mathematical model or experimental model, and secondly, it really gives us easier methods of analysis and design. So, can we say that the two methods complement each other? Otherwise, we can say that, well, there is no design method. If one design method was foolproof, the theory would have stopped there. we still continue with the research because no design method is foolproof. So, I will say, I like to comment that the two methods, why only two, even the other methods which have been developed but which we will not be able to take up in the class, all these methods complement each other, and therefore, a control system designer has to be conversant with all the methods of analysis and design which have been developed so far, so that he can develop some new methods as well, and I expect some new results from some of you if you take up control systems as your major area of professionalism. Okay. With this now, I think I can go to the basic steps of the frequency domain analysis in design. I will like to first take up the stability, then I will like to how to specify the performance, and then the design. You see, these are the three steps we have taken up in the root locus method: the stability, the performance, and the design. The root locus method had the stability could be determined by Routh-Hurwitz criterion or directly by the root locus. Here, a stability criterion called the Nyquist stability criterion is available to us, developed by Nyquist, a very important criterion. Rather, the frequency domain formalism is centered around this Nyquist stability criterion. This is the key feature of the total analysis and design method. Very important point, the backbone of the total frequency domain design methods. In the performance, well, in the time domain we had the rise time, the settling time, the peak overshoot, and so on. In the frequency domain, we will have the frequency domain's performance specifications. For example, one example I have already given, the bandwidth, the resonant peak of frequency response, as you will see, the resonant frequency, and so on. That is some of the frequency domain features. Here I said that, well, some of these features which have correlation with the time domain features are to be interpreted in the code in the time domain indirectly. This is the only limitation of the method. The design, yes, we had the lag compensator, the lead compensator, the lag lead compensator in the time domain or with the root locus method. You will find that all these basic compensators for which the op-amp circuit has been given to you work satisfactorily when we go to the frequency domain design also, and the design method becomes easier. In the time domain, you always have been raising a question to me, whether in the tutorial class or in the theory class, as to what happens to the dominance condition. If the dominance condition is not satisfied, how do we proceed? So, you can appreciate more or less you are entering into a trial and error design cycle, and when you repeat your questions to me again and again, I end up with the answer that if you cannot achieve this, well, I do not have any other tool with me. In that particular case, you have to either accept the design or reject the design, because there is no other tool with me other than the trial and error which you can carry out. But you will find that when you go to the frequency domain, the trial and error, though there, but is reduced considerably. All those questions which you had been raising to me will get reduced when we go for lag compensator, lead compensator, or lag lead compensator in frequency domain. Okay? So, these are the basic features of the frequency domain design analogous to the root locus design which we are going to take up, and therefore, without spending more time, I get started with the first feature, the Nyquist stability criterion. The complete rigorous proof I will avoid for want of time, but I think I will be able to make you appreciate the basic idea behind the criterion. It depends upon complex variable theory, particularly the principle of argument. I like to explain the criterion this way. Let me take up, yes, I really need your attention on this point, because the rigorous mathematics is being avoided. Only intuitively I will make you understand this particular criterion and its application. Application will be straightforward. Try to understand the basic concept behind it. I take this as the closed loop system, a general single loop system. In that particular case, I know Ys over Rs is equal to Gs over 1 plus Gs Hs is the closed loop transfer function of the system. Okay? Please see, help me. The denominator of this function is 1 plus GSHS. If I say, see my statement please, if I say that there is no point in the right half of S plane, say this is the S plane, sigma j omega, this is the region I am considering, including the imaginary axis. If there is no point in the right half of the S plane including the imaginary axis for which 1 plus GSHS equal to 0, in that particular case your closed loop system is a stable system. You see that I am twisting the characteristic equation statement a little because I want to apply this in this way when I come to Nyquist stability criterion. I repeat this point that this is the S plane I have considered. In this S plane all the S points are there. You consider the region in the right half of the S plane including the imaginary axis. The marginal stability case, initially let me talk of instability, let me take this as unstable case. So that by stability will mean that all the closed loop poles lie in this particular region, the left half of the S plane. This is my stability definition. Marginal stability I am taking it to the unstable region. Okay? So my statement which I gave, I repeat here that if there is no point on the imaginary axis or in the right half of the S plane for which 1 plus GSHS equal to 0, in that particular case I say that the system is stable. I hope this point is well taken. Okay? Fine. Let me talk of GSHS. What is GSHS? GSHS is open loop transfer function which is known to me. It consists of the process transfer function, maybe the compensator transfer function, the sensor transfer function or any transfer function in the loop, but open loop, the loop is broken. So it means GSHS is known to me. Okay? So this GSHS, let me assume for the present, is a ratio of two polynomials, the NS polynomial and the del S polynomial. And all the GSHS we have encountered so far are really the ratios of the two polynomials except the case of dead time, where e to the power of minus s tau d we have taken. So initially for convenience, though the result will be applicable to other functions including dead time, initially for convenience let me take GSHS to be a ratio of two polynomials, the NS polynomial and the del S polynomial. So you will please note I say that the zeros of GSHS and the poles of GSHS are known to me. Please see that, because this is an open loop function, the process, the sensor, the compensator and all these transfer functions can be multiplied together to get me the value of GSHS, and hence the zeros of GS and poles of GSHS are known to me. This is nothing to investigate, this is a data given to me. This point may be stored in your memory that the particularly I am referring to the poles of GSHS are known to me. So you see that if the poles of GSHS are in the left half plane, the system is open loop stable, and if some of the poles of GSHS are in the right half plane, then the system is open loop unstable. But a system may be open loop stable or open loop unstable, it does not matter, because I want to study the stability under closed loop. My question is that the system under closed loop should be a stable system, because a feedback system or feedback principle has got the capability of stabilizing an otherwise open loop unstable system. So you see that if you are given an open loop unstable system, it does not matter. It means your plant is open loop unstable and you want to study the stability properties when the loop has been closed, that is under feedback. Whether the roots of delta S or the poles of GSHS are in the left half plane or in the right half plane, whether it is open loop stable or open loop unstable, the point I am re-emphasizing that this information is known to me and I am interested in the information on the closed loop system. Okay? So now I am interested to study the function 1 plus ns over delta S, please, which is equal to, as you see, delta S plus ns over delta S. I need your help here, please. Suppose delta S is an nth order polynomial. So, this is equal to delta S plus ns. The nth order polynomial, I assume, has been factorized to give you n poles, s minus alpha 1, s minus alpha 2 and s minus alpha n. Can you give me what is the numerator polynomial? What is the order of the numerator polynomial? I should be able to get the answer from you. I repeat my question, the denominator is known to you, it is in nth order. The numerator is not known to you in terms of factored form, though ns and del s are separately known to you, but delta s plus ns in factored form are not known to you, because this is nothing but the characteristic equation of the system which you want to investigate. So, my question was to you, what is the order of the numerator roots? N only. This point may please be noted, for very carefully noted, the order of ns has to be less than or equal to delta s for physical realizability of GSHS. After all, GSHS is a physical system and ns by delta s is the pole 0 form of the physical system. So, the order of ns has to be less than or equal to delta s. In most of the control systems, we come up with a situation where the order of ns is delta s, but to give it a complete mathematical picture, let me call it less than equal to delta s. So, if that is the case, delta s plus ns naturally at the most can be of order n, and hence this can be written as s minus beta 1, s minus beta 2, s minus beta n divided by s minus alpha 1, s minus alpha 2, s minus alpha n. This is 1 plus GSHS. Very interesting point, please. The criterion will, the principle of argument will follow from this point. 1 plus GSHS is in this form. Okay? It is a general one, right? And recall the point. The point is this, that if there is any s in the right half of the s plane or on the imaginary axis, so that 1 plus GSHS is equal to 0, in that particular case the system is unstable. This is what is our conjecture, on the basis of which we are going to discuss this mapping. So, when I say any s, consider this as the s plane, sigma, j omega, consider any point s here or anywhere. You see, this is a complex variable, sigma plus j omega. If I substitute this in the expression g sigma plus j omega, h sigma plus j omega, I can say that this gives me a point w, which is again a complex variable, and let me call this point as u plus jv. And therefore, if I take what is called another complex plane, the w plane, whose real axis is u and imaginary axis is jv, can I say that this point maps into a point in the w plane under the function 1 plus GSHS. So, it is a mapping, and for a rational function, though we do not go to deep mathematics, it is actually 1 to 1 mapping. So, the function we are considering, it is a 1 to 1 mapping. For every point here, there is one and only one point here in the w plane. So, it means actually, let me now change the language. Now. I say that I really want to see the mapping of the entire right half of S plane under the function 1 plus GSHS equal GSHS to see whether origin is covered by this mapping. Is it all right? Please, equivalently, I want to consider the imaginary axis and the right half of the S plane completely, and I want to map this onto the W plane using the function 1 plus GSHS to see whether the origin of the W plane is covered or not. If the origin of the W plane is not covered, the system is stable, and if it is covered, the system is unstable. This is the equivalent statement of what I have been giving over earlier. So, it means I am going to consider the mapping 1 plus GSHS, and since every map, I need your attention here, every map corresponds to a point in the W plane, I will like to say that any contour here, a contour is nothing but a connection of points, will give me a contour in the W plane, surely, because there is a 1 to 1 mapping. Since there is a 1 to 1 mapping, a contour in the S plane, a connected graph in the S plane will give me a contour or a connected graph in the W plane under the function 1 plus GS HS. Okay. So, I am actually mapping from S plane to W plane under the function 1 plus GS HS. Okay. One point may please be noted, and that point is this: what is after all your interest? You are really not interested to see that under this map what is the magnitude of each and every point correspondingly in the W plane. You are really not interested. Your interest is to see only the covering of, or only what is the behavior of the system around the origin of the W plane, whether the W plane origin is covered or not. So, you see that if actually one-to-one mapping is to be obtained, it becomes a very difficult proposition and the Nyquist stability criterion will lose its importance. We are really not interested one-to-one mapping quantitatively. We are interested in one-to-one mapping qualitatively only, because our interest hinges around the origin of the W plane. Okay. So, you see that, and this we see any contour in the S plane will map into a contour in the W plane. This also should be clear. Okay. If this is appreciated, then a question will follow. The answer to this question will convince me whether my point is well understood or not. I take just tentative contour in the S plane and let me traverse this contour in the clockwise direction. Help me what will happen in the W plane or 1 plus GS HS plane. This is the contour, any tentative contour I have taken. The only thing I do is this, that one of the zeros at S is equal to beta 1 I enclose in this contour. All other zeros, let us say beta 2, pole alpha 1, another pole alpha 2 are outside this contour. See my point please. As I said that any contour in the S plane will give me a corresponding contour in the W plane. Without justifying as to why did I take this, I take a contour, and this is a closed contour with the only point that a 0, one of the zeros of the function 1 plus GS HS is enclosed in this contour, and all other zeros and poles lie outside this contour. Now, as I said, I am not interested in the quantitative mapping. I am interested only in the qualitative mapping, and comment on the qualitative mapping of this contour on to the W plane contour under the function 1 plus GS HS, whose poles and zeros are shown to you. This you know is S minus beta 1, S minus beta 2 and so on, S minus alpha 1, S minus alpha 2 and so on. This is your function 1 plus GS HS, and I want you now to comment as to what will be the qualitative nature of the contour in the W plane when S plane changes from point to point all along this particular contour. Okay. Let us get started. Let us first take beta 1 itself. You see, after all, when you take S, you take S is equal to S1. What will you do? You will substitute S is equal to S1 in this. So, it means S1 minus beta 1, S1 minus beta 2 are the numerator phasors. S1 minus alpha 1, S1 minus alpha 2 are the denominator phasors. Multiply the numerator phasors divided by the multiplication of the denominator phasors, that gives you the magnitude of the corresponding point here. And how about the phase angle? Add up all the angles of these phasors, add up all the angles of these phasors, take the difference, and that is the angle of this point here. So, the S is equal to S1 point using this particular function 1 plus GS HS can suitably be converted into this particular point W1 here. This is the W1 point, and how do you get it? You just take up the phasor. This is your phasor S is equal to S1, S1 minus beta phasor. Similarly, this is S1 minus beta 2 phasor, this is S1 minus alpha 1 phasor, this is S1 minus alpha 2 phasor and so on. Since graphically you are working with a graph, you need not do the calculations, you just measure all these phasors, multiply the numerator phasors, multiply the denominator phasors, divide, gives you the magnitude. Angles minus these angles gives you this angle, and hence there is a corresponding point. So, this way, if I keep on travelling along this particular contour in the clockwise direction, I will get the corresponding points over here and I will definitely get a closed contour in the W plane. Okay? And I say that, well, quantitatively I am not interested in. Now qualitative picture, just see. Look at individual phasors. What will happen with the S minus beta 1 phasor? S minus beta 1 phasor, as you travel along this particular contour, contributes an angle of minus 2 pi, you can see. Start from this point, traverse along this, and the total angle contributed is minus 2 pi. Okay, come on, look at the S minus beta 2 phasor, start from here, go back to this and come back to this. The total angle contributed by S minus beta 2 phasor is 0, because if this is positive, there is a corresponding negative angle. Please see, if this side is positive, there is a corresponding negative angle. So you see that the S minus beta 2 phasor, if you take, as S traverses along this particular route, the net angle contributed by S minus beta 2, this is the crux of the total Nyquist stability criterion. Please say that if there is a 0 enclosed in it, it is going to contribute an angle of minus 2 pi, and if all other poles and zeros phasors outside do not contribute the net angle as far as this particular contour is concerned. So qualitatively I can say that whatever may be the shape, you see, when you travel along this particular route, the contour is going to encircle and the origin once and only once, and that too in the counterclockwise direction, because the angle is minus 2 pi. See this point, please. On this I am going to base the criterion, and the criterion will become very simple. You see that if there is a 0 enclosed here, by this S plane contour which you have tentatively taken, in that particular case I find in the corresponding S plane contour there will be a contour, shape may be anything. I am not going to do the calculations because I am not interested in the shape, but this is sure that this particular contour will enclose this particular minus 2 pi. Minus 2 pi will be, sorry, what is the angle, please help me please. This, if you travel from this side to this side angles are minus 2 pi, sorry, clockwise direction, because this angle if you are taking, the net angle is this way, the angles are taken negative and minus 2 pi. So it means this is going to encircle the origin in the clockwise direction once. Now you just imagine that, repeat this performance and say that there is a pole now in the origin in this particular enclosed path. There is a pole and not a 0. All other zeros and poles are in the outside this particular contour. All other poles and zeros are outside this. Help me please, what will happen to the encirclement when you go along this particular contour? Yes, please see that now also the angle is minus 2 pi, but since it is a pole, the net angle contribution is reverse of that, and therefore it will become plus 2 pi as far as net angle contribution to 1 plus GSHS is concerned. The net angle contribution to 1 plus GSHS, I hope this point is very clear. Angle is minus 2 pi as you traverse it this way in the clockwise direction, but since this particular pole is in the denominator of the function 1 plus GSHS, so the net angle contribution is plus 2 pi, and therefore the net encirclement of the origin is going to be once in the counterclockwise direction. And now extend this particular situation. This is your contour, it has got 2 poles and a 0. 2 poles and a 0. So in that particular case, please see that 2 counterclockwise and 1 clockwise, the corresponding thing will be that there is one net rotation in the counterclockwise direction, because the 2 counterclockwise rotations are given by poles and 1 clockwise rotation is given by 0, and therefore the total counterclockwise rotations are 2 minus 1 is equal to 1. Okay. So what you and how about this? Please see, what I want to say is this. Now I think the picture should be clear. Through this the picture should be clear now, and I hope you will be able to state the Nyquist stability criterion now. Let me say I will leave it open and try to get the criterion from you as to how to test the stability. What I want to say is this, that the S-plane contour which I have thought of is now the complete right half plane, though it is an infinite contour. How to handle this situation, I will come to this later. The complete region, and therefore, this is the contour which I want to travel in the clockwise direction. Okay? And suppose you have got the map. This is the corresponding map. It encircles twice, thrice, we do not know. Suppose you have got the map. So, please tell me as to what is the, how to check the stability. Suppose in this particular contour, just suppose that there are how many p poles of 1 plus GSHS. You will please recall that these p poles of 1 plus GSHS are nothing but the poles of GSHS which are known to you, and hence the value p is known to you. Capital P I am taking. P poles of 1 plus GSHS. These are not the closed loop poles. This point may please be very well understood. These are not the closed loop poles of the system. The function under consideration is not Ys by Rs. The function under consideration is 1 plus GSHS. So, it means if there are p poles of 1 plus GSHS in this particular region, and let us say Z zeros. What are the zeros of 1 plus GSHS? Are you able to appreciate this point, that zeros of 1 plus GSHS are nothing but the closed loop poles of the system? Try to see this point. Your zeros are not known to you. Zeros of 1 plus GSHS you can work out in your own way, and you will find that zeros of 1 plus GSHS are nothing but the closed loop poles of the system, and poles of 1 plus GSHS are nothing but the open loop poles of the system. So, if there are p poles, a value which is known to you, and z zeros, a value which is not known to you, and you have got the 1 plus GSHS map of the function in that particular, and let us say that there are n encirclements of the origin in the counterclockwise direction. Can you give me the equation, please? I want the equation from you. There are p poles of 1 plus GSHS in the right half plane and z zeros, and there are n encirclements of the 1 plus GSHS contour of the origin by the 1 plus GSHS contour. Can you give me an equation between n, p and z? P minus z, that is fine. This is what is the Nyquist stability criterion. Please, how to use it, how to interpret it, we are going to see. But the Nyquist stability criterion is this, and the importance of this you will see that the total frequency domain design is based on Nyquist stability criterion. It says n is equal to p minus z, that is the total counterclockwise encirclements of the W plane of the origin of the W plane contour is equal to p, the number of poles of 1 plus GSHS in the right half plane, minus z, the number of zeros of 1 plus GSHS in the right half plane. Okay? This should be clear now. Now, you see that the only thing you have to do is now get a map of the this particular contour. Getting a map of this particular contour and counting n is the only thing left. Counting n. So, it, yes please.
What about poles and zeros on the contour?
On the contour, yes, it is a very important point, please, though I thought that I am going to exemplify it. You see, when I take this contour, his point is this, can you tell me what will happen if there is a pole or a zero, pole particularly, zero will not create any problem, but if there is a pole on the contour, what? You are going to get infinity, corresponding infinity, and the corresponding mapping does not exist. So, initially when I am describing this particular situation, let me describe this under the assumption that there is no pole on the contour. I will extend it what will happen when there is a pole on the contour. Okay? Because pole is that of an open loop system, and you know beforehand whether it lies on the contour or not. You see, you know beforehand, so it does not create any problem as far as pole is concerned. Zeros will not create any problem, but pole will. And in the beginning, let me say that I am talking of only those systems for which there is no pole on this particular contour, and this information is known to me. For this there is no problem. You see the corresponding encirclements, and these encirclements will give you the value of n. The value of n known to you, the value of p known to you, and hence the value of z is known to you.
So, if there is 0 on the contour,
Yes.
that will include in z.
If there is a 0 on the contour, what will be its mapping?
The contour will pass through origin.
The contour in that particular case will pass through origin, and this actually is the case of marginal stability. So, this case also will come up this. That is actually if there is a this contour passes through the origin, this case corresponds to, as you have seen in this particular case, the zeros of the system, zeros of, sorry. Now tell me please, zeros of ns are known to you. Okay? Zeros of ns on the contour do not create any problem. Zeros of ns, because it is the zeros of 1 plus gs hs which are there, s minus beta 1, s minus beta 2 and so on. So as far as this statement that a 0 on the contour has no meaning, because the zeros of the closed loop system you do not know. The zeros of the function 1 plus gs hs you do not know, and the zeros of gs hs are only known to you, and the zeros of gs hs do not create any mapping problem.
So, what will be the problem created by a 0 of 1 plus GS?
That is an analysis problem that we will see. That is, you see, this statement at least let us revise, that the Nyquist contour passing through a 0 of GSHS doesn't matter. This I am revising. This is another point. That is, if this contour passes through the 0 of the origin of the 1 plus GSHS contour. This is a point I am going to explain. This is a different point. So it means we are left with 2 points now to be explained. One, if there is a pole of GSHS on the contour, because you get correspondingly infinity. And second, if this contour passes through the origin. But for these 2 points everything is alright. Please see. These are the 2 points which need explanation. But if there is a 0 of GSHS on this particular contour, that doesn't create any problem. That should be clear. That is what I wanted to revise. So your singularities or the problem cases are there when there is a pole of GSHS on the contour, Nyquist contour. Let us call this as a Nyquist contour. This particular contour which you have taken, I name it as a Nyquist contour. So if there is a pole of GSHS on this, yes, there will be a problem. And the second point of interpretation is this, that if it passes through the origin, keeping these 2 points pending, assuming that none of these 2 conditions exist, let us see what is the interpretation of Nyquist stability criterion. It says that n is equal to p minus z. You count n from here. You count p is already known to you. Therefore, from this equation you have z. So in this particular case, you find that these many zeros of 1 plus GSHS are in the right half plane, and hence not only instability but some additional information about instability is also given, as was given by Routh stability criterion. You recall, it gave you the number of poles in the right half plane. This information is available in the Nyquist stability criterion also. It gives you information on the number of zeros of 1 plus GSHS in the right half plane, which is equivalent to number of closed loop poles in the right half plane. So it means the procedure is this, that you take this contour, map it into this point and see the number of encirclements of the origin and apply this particular algorithm to check whether the system is stable or not. If it is unstable, how many closed loop poles lie in the right half plane. Okay. If this is clear, then help me please equivalently. If you have an open loop stable system, what is the condition of stability of the closed loop system? I repeat my sentence for you to absorb. For an open loop stable system, means p is equal to 0. What is the condition of stability of the closed loop system? The case most often we come across. I am making this statement because this is the case we come across most often. For what is the condition of stability of the closed loop system for an open loop stable plant? Yes? I should get the answer from you. I will wait please.
0 should be on the left half plane.
No. In terms of encirclement I want. What should be the condition of on the W plane contour? If your original system is open loop stable. That is, the open loop system is open loop stable.
There should be P encirclements.
There should be, when I say open loop stable means P is equal to 0. This is what I wanted you to identify. There should be no encirclements of the origin. That is why I said that I repeated this statement, an open loop unstable or open loop stable system. An open loop stable system means capital P is equal to 0. Note this point please. You will, 90% cases will be of this nature, of this statement. That is why I am making this. These Nyquist stability criterion should be clear. But most often we will come across this statement that an open loop unstable system, for that P is equal to 0. So it means if you have a case for which P is equal to 0, in that particular case, the system is stable. If, and you know that for stability Z equal to 0, so Z is the closed loop poles in the right half plane. Z is equal to closed loop poles in the right half plane. For stability Z has to be equal to 0, so it means the statement for open loop stable system, the stability requires that the Nyquist contour, the Nyquist plot, or this particular plot in the GSHS plane, let me call it Nyquist plot. The Nyquist plot in the W plane does not encircle the origin. Okay? Nyquist plot in the W plane does not encircle the origin. That is, for example, this could be the possibility. If this is the contour, P is equal to 0, there is no open loop pole in this particular region, your plot may be of this type. It cannot encircle the origin. Your plot may be of this type. Okay, what is this plot? This plot is a plot of 1 plus GSHS function. Please see that, since I know that the time I'm looking at the watch. 1 plus GSHS plot is difficult to make. I hope you won't mind if instead of making 1 plus GSHS plot, I make only GSHS plot and encirclements of the origin. Instead of looking at the encirclements of the origin, I look at the encirclements of the point minus 1 plus J0. That is, I shift the entire plot by 1 unit towards left. So in that case, the concluding statement, an open loop stable system is stable under closed loop operation if and only if the plot of GSHS does not encircle the minus 1 plus J0 point. This is the crux of the total criterion, and our additional lectures are going to be based on this criterion only. And how about the other case? You see, if there is a case of open loop unstable system, tell me n is equal to P minus Z. What is the condition of stability? Statement, please, if you want to go, you give me the right statement. An open loop unstable system with P is equal to 1. Let us say a situation of this type, S plus 2 over S plus 1 into S minus 1. You find that there is one pole in the right half plane. It is open loop unstable system. So it means capital P is equal to 1. Tell me what is the condition on GSHS plot for stability? It should encircle minus 1 plus J0 point once. It's not enough. Once in counterclockwise direction. Statement once is not enough, please. For this system to be stable under closed loop operation, the GSHS plot should encircle minus 1 plus J0 point once in the counterclockwise direction. This is what is the Nyquist stability criterion. Thank you very much. The applications will follow in the next lecture.